Okay, so let us continue our discussion on some of the basic flow solutions. Earlier we had looked at how we can obtain an expression for hydrostatic pressure drop from the Navier-Stokes equation, and then we also looked at flow of a thin film of liquid in an inclined plane. Now we will look at Couette flow situation. In Couette flow we have either one or more plate moving related to each other, okay, that actually creates flow. There is no pressure gradient, there is no body force, and the flow occurs simply because of the movement of the plates. Okay. The applications of Couette flow could be in rheology, where we can determine a viscosity of a fluid. Typically we have two concentric cylinders, and we would have a fluid present in the annular space whose viscosity we want to determine, and if we can maintain a constant speed of rotation, the torque that is required to maintain that constant speed will be related to the viscosity. Okay, that is how we would be able to determine the viscosity. Now here we will look at a simple case, flow between two parallel plates where one or two plates are moving. Okay. So we look at Couette flow. So here we would have two parallel plates. So this is the origin here, x, y, and this is at plus h, this is at minus h. This plate is moving at velocity of uh, and this plate is moving at velocity of ul, and we have gravity acting in this direction, and the del p over del xi is 0. So there is no pressure gradient. Okay. And we make certain assumptions. We assume that the fluid is Newtonian, there is no pressure gradient acting, and there is no body force present. Okay. And flow is unidirectional and uniform. So the velocity component and the gradient of the velocity are orthogonal to each other. So the convection term drops up from the Navier-Stokes equation. So with that assumptions, so we have Newtonian assumption, Newtonian, no pressure gradient, okay, no body force, and uniform flow. Okay. So under those assumptions, our Navier-Stokes equation, if you write, the u will be a function of y only, right. We are talking about infinite parallel plates, so the z coordinate will not be important, and u is a function of y only, u is not changing along x direction. So under that assumption we can write the Navier-Stokes equation, rho into del u over del t plus u del u over del x equal to rho into fx minus del p over del x plus eta into del square u over del x square plus del square u over del z square plus del square u over del y square. So here another assumption is flow is steady. So this term would drop off. The flow is uniform, the velocity and the gradient are orthogonal, so this term will drop off. There is no body force term, and u is only dependent on y. So, del u over del x is 0. Also we can consider that the z components is infinite, this is also not important. Okay. So, the equation we get, there is no pressure gradient, so this term will be 0. So, we say that the viscous force del square u over del y square eta del square u over del y square is going to be 0, right. So, now if we talk about the boundary conditions, the velocity on the top wall, say plus h, will be u, here if you look at, will be uh, okay, and u at minus h will be ul. Okay. Now this equation, if we integrate this equation, we get u of y as c1 y plus c2. Okay. So if you apply the boundary conditions, you would get that u of y will be uh plus ul divided by 2 plus uh minus ul divided by 2 into y over h. Okay. So this is how the velocity is going to vary in the y direction. Okay. So this equation satisfies the boundary conditions at both the top and bottom walls where the velocity vanishes, and the velocity is linear in linearly dependent in the y direction. Okay. So if you look at this situation, if you try to plot how the velocity is varying, it would, let us say uh is greater than ul, then it will vary something like this, okay, where this will be uh and this will be ul and this will be varying linearly. Okay. Now from here, from the velocity profile, we can find out what the value of shear stress is. Okay. So if you write the shear stress tensor, tau ij will be equal to, so let us move on to the next page. We can write tau ij is equal to the 9 components tau xx, tau xy, tau xz, tau yx, tau yy and tau yz, tau zx, tau zy and tau zz. So if you look at the relation between stress and strain, this will be 2 eta into epsilon ij. This is what we can see from the constitutive relationships. So this will be 2 eta into the strain components. So epsilon xx, epsilon xy, epsilon xz, epsilon yx, epsilon yy, epsilon yz, epsilon zx, epsilon zy, epsilon zz. Now if you write down the expression for the strain, the matrix should look like this. It will be 2 eta, you write the strain in terms of velocity components, so del u over del x, and this will be eta into del u over del y plus del v over del x, and this will be eta into del u over del z plus del w over del x, and the second one will be eta into del u over del y plus del v over del x, this will be eta into 2 eta into del v over del y, and this will be eta into del v over del z plus del w over del y, and the last row would be eta into del u over del z plus del w over del x. This will be eta into del v over del z plus del w over del y, this will be 2 eta del w over del z. Now, in this general stress tensor, if you put down the values for the velocity gradient, then you would see this will be 0, this will be eta into UH minus UL over 2H, this will be 0, this will be eta into UH minus UL over 2H, 0, 0, all others will be 0. So, what you see here, only tau xy and tau yx exist. Okay. So, you can write tau xy, tau yx will be eta into UH minus UL over 2H, right. Now, from this equation you can see that if the velocity of the upper plate and the lower plate are equal, if UH equal to UL, then the shear stress is going to vanish. Okay. So, what that means is that if you have two plates here, okay, and this is moving at u, this is also moving at u, how do you expect the velocity profile to be? If you go to this velocity profile equation, this term will drop off. So, this will be 2u over 2, so it will be u, right. So, the velocity will stay at u throughout. Okay. So, the shear stress is going to drop out. Now, how we can define Reynolds number in this case? In a flow through a pipe of uniform cross section, we know that the Reynolds number will be rho u d over mu, right, or eta. In this case, what should be the velocity scale? One plate is moving at UH, the other plate is moving at UL. Okay. So, the way we should correctly represent the velocity scale, that should be UH minus UL. Okay. The relative velocity should be the scale how the flow velocity need to be correctly represented. So, the Reynolds number could be correctly defined as, so the Reynolds number is normally rho u L over eta, right. So, that is how Reynolds number is defined, it is inertia to viscous. So, in this particular case we can define it as rho into u will be UH minus UL into, so the spacing between the plates, this is going to be 2h, each plate is located at plus h minus h, right. So, this is going to be 2h divided by eta. So, that is how the Reynolds number is going to be defined in case of Couette flow. It has been found that for Reynolds number less than 100, the the velocity profile obtained by this model matches very well with that obtained from experiments. So, which is a case in microscale flow situation, quite often the Reynolds number would be less than 100. So, the analytical result obtained here for the Couette flow situation is applicable to microscale flow situation. So, for Reynolds number less than 100, the analytical results for velocity matches quite well with experimental results. Okay. And this is the case which is valid for microsystems. Now, if you want to know what should be the value of the force that is applied on the plates in order to move the top plate at UH and the bottom plate at UL, we can determine that from the shear stress value. Okay. So, we can determine the force required. The force required can be determined by, so F x top or bottom would be eta into UH minus UL divided by 2H into AP. So, this is the shear stress, okay, eta into UH minus UL divided by 2H. So, shear stress into the area of the plate, okay, that is the force that we would require to move the plates relative to each other. Also, from this equation, knowing the area of the plate, knowing the velocities, knowing the force that is required, we can also estimate eta for a practical situation. Okay. So, this equation can also be used to measure eta for eta of a fluid. Okay. Right. Next, we move on to talk about Poiseuille flow. Okay. So, in many micro scale flow situations, we have flow through channels that have constant cross sectional area. The cross sectional area does not change along the length of the channel, okay. And that is the case what is discussed in Poiseuille flow. And again, Poiseuille flow is a special case where the cross sectional area is circular in shape, okay. But in micro channel, we have channel cross sections of different shape. We have rectangular channels, triangular channels, elliptical channels. So, different channel shapes we can encounter in micro channel flow situations. So, let us first talk about how we can obtain a flow solution for a channel cross section of any arbitrary shape. So, we will not worry about what could be the channel shape, it could be any arbitrary shape, and we would see how far we can push to obtain an analytical solution for that. Okay. So, let us talk about Poiseuille flow. Okay. So, here we talk about channel of arbitrary cross section that does not change along flow direction. So, the cross section does not change along flow direction. Okay. And here we make some assumptions. We say that the flow is uniform, it is steady, and the fluid is Newtonian. Okay. Under that assumption, we can obtain an analytical solution. So, we can say steady flow, Newtonian, uniform, but here pressure gradient exists. Okay. So, in Poiseuille flow situation, we would have the pressure gradient which is non-zero, and that actually drives the flow. Okay. So, the pressure gradient exists in case of Poiseuille flow. So, here we take an arbitrary channel shape. So, it could be, let us say, of this shape, and we have the channel and the shape does not change across different section, Okay. Let us say this is x direction, this is z direction, and this is y. So, the cross section is in the yz plane, and this is the cross section denoted by C, and the boundary is denoted by del C, and here we have P at 0. So, this is let us say x equal to 0, right. So, x equal to 0, P 0, which is the inlet pressure, is let us say P star plus delta P, okay. And here P at L is going to be P star. So, here under that assumption we can say that here the channel section is not changing. So, channel section or cross section not changing along x, okay. And so, here C represents the cross section of the channel and delta C represents the boundary, right. And since the flow is uniform, we have u x is not equal to 0 and u x is a function of y and z, okay. And the other components u y and u z are 0, okay. So, we can write down the Navier-Stokes equation, okay. So, first we write down the x component. So, the x component would be rho into del u over del t plus u del u over del x equal to rho f x minus del p over del x plus eta into del square u over del x square plus del square u over del y square plus del square u over del z square. Now, for steady flow this term would drop to 0, this is uniform. So, the velocity and the gradient are orthogonal, this term drops off, the body force is 0, okay. And here you see this u does not vary along x. So, this term will drop off. So, we have an equation which looks like this. So, eta into del square u over del y square plus del square u over del z square will be dp over dx. Let us still say del p over del x, okay. Now, the x component, the the y and z momentum equation, the y and z momentum equations, we would get delta p over delta y will be 0 and delta p over delta z will be 0, because the other velocity components u y and u z are 0, right. So, what does this mean? This means that pressure is a function of x only, right. Pressure is a function of x only, right. Now, if you look at this equation, let us call it equation 1, the left hand side says that the function is a is dependent on y and z. Here the right hand side the function is dependent on x, okay. So, in an equation if the left hand side is function of y and z and the right hand side is function of x only, we can say that both sides can only be equal if they are equal to a constant, okay. So, since equation 1 left hand side function of y and z and right hand side function of x, we can say that both sides equal to a constant. That is the only way this is going to be possible. So, in that case, so we can say del p over del x, okay, which is the right hand side, is a constant. What that mean? That means that pressure is varying linearly along x, right. So, pressure varies linearly along x. Now, we have the boundary conditions. P at 0 is going to be P star plus delta P and P at L is going to be P star. So, if you apply that to this equation, this delta P over del x is constant, what we get is P of x is going to be delta P over L into L minus x plus P star. Okay. So, this satisfies both these boundary conditions. So, if you put x equal to 0, the pressure will be P star plus delta P, and if x equal to L, then pressure is going to be P star, right. So, in that case our equation, the equation 1, this equation would become, so the equation 1 become del square u over del y square plus del square u over del z square equal to minus delta p over eta L. Okay. So, this is an equation, this equation is going to be valid for different cross sections. Okay. This is independent of the cross section of the flow, okay, for any Poiseuille flow, right. So, here we can say that the no slip boundary condition is valid for u y z equal to 0 when y z belong to delta c. So, when y z lie on the boundary, which we said here delta c is the boundary here, when y z present on the boundary, the velocity is going to be 0, that is the no slip boundary condition. So, in that case we can write the expression for the velocity. So, u y z can be written, and so this is basically, this equation is basically a Poisson equation, right. So, this is a Poisson equation, in Poisson equation in 2D, right, and we can obtain a general solution using the Dirac notation. Okay. So, we can write u y z using Dirac notation using eigenfunctions. So, in a general sense, if you have a Poisson equation which looks like this, del square f r equal to minus g r, okay, where this is a unknown field, okay, and this is known, right. This equation is similar to the Poisson equation that we see here. So, this is unknown and the right hand side is known. Okay. So, here we can obtain a solution using eigenfunction which something looks like this. So, function f, this is called the Couette of function f, which will be summation n equal to 1 to infinity, this is called bracket of phi n into g divided by k n square into the ket of phi n. Okay. So, this is called, this is the eigenfunction bracket notation, and this is known as the ket of phi n, and phi n being the eigenfunctions, and here this one is the ket of the field, unknown field f. Okay. So, that is a standard way how eigen solutions are obtained. Okay. If you have an equation in this form, you can write down the solution, direct notation of the unknown field in this way. Okay. So, similarly, if you look at this equation, we will be able to write down the direct notation for the velocity field u. Okay. So, we can write the direct notation for u y z like this. So, we can write that u, which is a function of y z, will be equal to delta p over eta L into summation n equal to 1 to infinity phi n 1 divided by k n square into phi n. Okay. So, this is the ket of phi n, this is the bracket of phi n and 1, because your function g r here is delta p over eta L. Okay. And you have taken delta p over eta L out, this function here is 1, this is the known function, and k n square are the eigenvalues. So, these are the eigenvalues, and this is the eigenfunctions, and this is the direct notation for velocity field. Okay. So, this is a general solution for the velocity irrespective of the cross section that we are talking about. Now, from this we can also determine the expression for the flow rate. Okay. Using the eigenfunction, we can relate the flow rate to the pressure gradient. Okay. How we can do that? So, the flow rate q, okay, so the flow rate q can be written as, q will be integration over the cross section u y z into dy dz, right. This is the expression for the velocity. Now, in general sense, if you look at eigenfunctions, the integration of c dy dz into f u y z f y z into g y z can be written as the bracket of function f into g, which can be represented as this. So, n equal to 1 to infinity 1 over k n square. So, this is the eigenvalues k n, right, and into the bracket of phi n 1 into bracket of g phi n. So, this is the general formula that we know from eigenfunctions. So, similarly, here we can write an expression for q. So, q could be, so in this case f is the velocity field and g is going to be 1, right. So, we can write q to be dy dz into u y z into 1, okay, that is the G. So, which will be equal to the bracket of 1 into U, which can be written as delta P divided by eta L into summation n equal to 1 to infinity 1 over the eigen values k n square into phi n 1 into 1 phi n. Okay. So, this is the general expression for the flow rate. Irrespective of the cross section, you can write the flow rate in this form, right. Now, we would try to non dimensionalize this term that is within the summation. So, you try to non dimensionalize this term, non dimensionalize this term. How we can do that? Okay. So, if you look at this expression here, okay, the velocity expression, here you can find out the units of each of these, and it will turn out that the unit of the eigenvalue square is of the order of 1 over L square. So, how we can check that? We can do it this way. We can write u y z equal to delta p over eta L summation n equal to 1 to infinity into phi n 1 bracket divided by k n square into the ket of n, right. This is what we know from here, right. So, if you look at the unit of each of these term, this is meter per second, okay. This is delta p is Newton per meter square, and eta is Pascal second, right. So, Newton meter square will go here into second, and this will be L will be meter. These are the functions, okay. So, they are dimensionless. So, you would see that k n square, this unit here has to be 1 over meter square, right. Then only it will be dimensionally correct, okay. So, the k n square, so this has to be meter square, then only it will be valid. So, this will get cancelled, and this Newton will get cancelled, this will cancel with one of the meters. So, this will be meter per second, right. So, what we get from here is that the eigenvalue, square of eigenvalue, okay, should scale as 1 over meter square, right. And it turns out that you can multiply these eigenvalues, k n is multiplied with another length scale called r, okay. So, to make this term non dimensionalized, okay. So, instead of k n square in the denominator, you would have k n into r square. So, that would make this term dimensionless inside the bracket, right. So, this is important to understand. Then if you look at the dimension of these two terms here, right. Now, before we go to that, we can say that we can, let us write down this equation here, q equal to delta p over eta L n equal to 1 to infinity 1 over the eigen value square into phi n 1 into 1 phi n, okay. So, if you do a similar dimension analysis, meter cube per second, and if you try to write down the dimension for this, what and also the dimension for this, what you would see is the product of these two would scale as the meter square. Okay. So, and this term is would call as the effective area which is A, whereas this term would call as effective radius, Okay. So, you can write the R turns out to be half of the hydraulic diameter. It turns out that R is half of the hydraulic diameter. So, in that case you can write R to be 2 into area of cross section over perimeter. Okay. So, you can write the expression for R, right. Now, for a circular cross section, the R will be equal to A. So, now we can write down the expression for Q as follows. So, you can write Q to be 1 into U, 1 U, the bracket of 1 and U, which is delta P over eta L into R square A into n equal to 1 to infinity 1 over the square of the eigenvalues, sorry, k n into, here you will non dimensionalize the term. So, k n into R square, and here you would have another A n over A. Okay. So, A n is the effective area, this is A n, okay, and A is the area of cross section, right, and R is the effective radius. Okay. So, this is how you can non dimensionalize the terms inside the summation, okay, to obtain a value for an expression for the flow rate. Okay. So, for most of the micro scale flow situation, it has been found that the numerical value of the terms inside the summation is approximately equal to 1 over 8. Okay. This has been found, whereas for a circular cross section the value is exactly equal to 1 over 8. Okay. So, this term has been found, the value is about 1 over 8 for different cross sections and equal to 1 over 8 for circular cross section. So, we can write the expression Q as follows. So, we can write 1 over gamma into delta P over 2 eta L, 2 eta into L into A cube divided by P square, okay, cube of the area, square of the perimeter, where the R, the gamma is given by the summation term n equal to 1 to infinity into 8 divided by k n into R square into A n over A, and this term is found to be very close to 1. So, since you have multiplied 8 here, So, that has been taken care of for the value of the summation, and for any general cross section you can apply the flow rate expression, which would appear like this. Okay. So, you can try for circular cross section. Okay. R will be exactly equal to 1. So, for a circular cross section you can write the expression, this will be this will become 1. So, delta p over 2 eta L for a circular cross section, area will be pi r square and perimeter would be 2 pi into r. So, here you can write delta p into a cube over p square. So, this will be delta p divided by 2 eta L pi cube r 6, okay, because this is cube, divided by 4 pi square into r square. So, you would get pi delta p r 4 divided by 8 eta L, okay, and that is the expression for the flow rate through a tube of uniform cross sectional area. Okay. Now, next move on to to discuss the flow between two parallel plates of infinite length. Okay. So, let us discuss flow between infinite parallel plates. Okay. So, we have two plates here, okay, and let us say this direction is z, this direction is x, this is x equal to L, this is 0, and here the p at 0 would be p star plus delta p, and here p at L will be p star. Okay. And here we are talking about infinite parallel plates, that means the width of the channel is going to be large as compared to the height between two plates. Okay. So, infinite parallel plates so they are infinitely long, and we consider W over H to be greater than 1. Okay. So, under that assumption, since the width is greater than H, we can write symmetry condition, that means del u over del y will vanish. Okay. Our y is into the width, z is across the height. So, this will be vanishing. So, this is h, the plate height. So, in that case we can write down the Navier-Stokes equation. So, let us write down the governing equations, what we have found from our analysis here for a general cross section, okay, that is valid for every cross section. Just use this general equation here. So, if you use that general equation, we have del square u over del y square plus del square u over del z square will be equal to minus delta p over eta L. Okay. So, that is the general equation, right. Here this variation is negligible because we are talking about the width is large compared to the height. So, there is no variation along y direction. So, what we see here is del square u over del z square is minus delta p over eta L. Now, if you look at the boundary conditions, we can expect that u at 0 is 0 and u at height h will be equal to 0, and this is no slip. Okay. So, using that, if you apply these boundary conditions on this equation, we can get an expression for the velocity which will be a function of the z, delta p over 2 eta L into h minus z into z. So, this is a simple parabola. Okay. This is a simple parabola. What it says is that the velocity profile would look something like this. Okay. So, it will have maximum at the center and it will reduce to 0 at the walls. So, you can find out the maximum velocity u max. To find u max, you can say that del u over del z will vanish, right. So, in that condition you can find u max. So, u max can be found to be delta p into h square over 8 eta L. Okay. So, from the expression for the velocity you can find out the expression for the flow rate. Okay. So, the volume flow rate q can be found as integration of 0 to w dy into 0 to h dz into the u z, which can be found to be. So, q would be w h cube divided by 12 eta L into delta p, right. So, this way we would be able to find out the flow rate between two infinitely long parallel plates under the assumption that the width is large compared to the height. Okay. And this expression for the flow rate can be applied to flow through a rectangular channel, and the accuracy would be very good if the width of the rectangular channel will be about 10 times the height. Okay. So, when w is when w is about 10 times h, the error is only 7%, but if w is about 3 times h, the error goes to 23%. So, of width of channel width greater than 10 times the height, this expression for the flow rate is good enough. Okay. Similarly, you can compare the flow rate found by this formula here with the general formula which we have found out here. Okay. And we can see that you can do it yourself and you can check that the flow rates q will match, okay, q from here, let us say some equation x, equation x will match with q from equation y, where this is equation y, when w will be about 5 times h. So, this is something you can verify. So, with that let us stop here today.